Hi, my name is Anshu and welcome to my channel Bottleneck. This is a data structures and algorithms series. In this video, we are going to learn and implement AVL tree using Scala functional programming approach. So given we have an input 10, 5, 20, 15, 25, 12, 4 and 50. This is the output AVL tree that we are going to expect. Alright. Here E denotes the empty node and this is the structure that we are going to learn how it will be implemented. So first, what is an AVL tree? An AVL tree is a type of self-balancing binary search tree where each node has a balance factor and it is used to ensure the tree remains balanced, allowing efficient search, insertion and deletion. Balance factor is very critical point or very critical key value of an AVL tree. Each node in an AVL tree has a balance factor which is the height of the left subtree minus right subtree. It can be -1, 0 or 1. And this is the range of the balance factor for a tree to be considered as balanced. AVL tree are self-balancing, meaning that after every insertion or deletion operation, the tree is adjusted to maintain the balance factor of all nodes within the acceptable range. This is the range. The critical property of an AVL tree is the height difference between the left and right subtree of any node, that is the balance factor, which should be within this range. So AVL tree is also a height balanced tree. And this ensures the height of the tree is in logarithmic nature, which allows efficient search, insertion and deletion operation. When we talk about operations, we know that insert and delete are there. But when we say search, so in graph or trees, we have two kinds of operation. One is depth first search, another is breadth first search. In depth first search, we have in order, pre-order, post-order. In breadth first search, we have level order, traversal or the search operation, and we are going to see that in action once we implement this. All right. To balance this tree, we have some certain activities that we need to perform. That is the rotations. So we have four kind of rotations: right rotation, left right rotation, that is also known as LR rotation, and right left rotation, that is RL rotation. We will see them in action while implementation. Complexity. So the AVL tree has a complexity of O log n, where n is the number of nodes in the tree. This makes AVL tree suitable for use cases where efficient operations are required. Alright, so what are the use case of an AVL tree? The examples would be database indexing, auto completion suggestion, and many other scenarios where fast search operations are critical. Disadvantage, one of them is we have to maintain the balance factor and height, that is memory overhead. Secondly, because it is going to calculate the balance factor, so sometimes it is slower to have this insertion or searching operations given the kind of data that we are dealing with. All right. So said that, let's begin the implementation. I have divided this video or the AVL tree into two parts. In part 1, we will be implementing the basic structure of AVL tree, and we'll also implement the empty node. In part 2, we will implement the actual node of the AVL tree which has non-empty values, and we will also see the traversal techniques. All right, so let's begin. So it's going to be a sealed trait that is of type tree of A. First thing that AVL tree will have is a value that will be of type A. Next is the left node, which will be of type tree of A. Alright, it is going to be capital. Second thing is going to be def right, that is again type tree of A. Well, alright, so these are the three vital elements. Then we need height, that is going to be type of int. Then we have a balance factor, that is again going to be a type of int. Now let's make it camel case. All right, what else do we need? We need the rotations. So first is rotate right, that is going to return a tree of type A. Then we have rotate left, that will also return the tree of type A. Then we have rotate left right, that is also again going to return a tree of type A. And finally we have rotate right left, that is also going to return a tree of type A. Alright, now given that we have all this, we also need something. Before we know that what we are going to do, we need to wrap this all rotation inside one method, that is going to be balance, which will also return a type of tree, tree of type A. So what we will do is inside balance we will be doing or checking for the balance factor and returning a tree whether it is balanced or not. If not balanced, we will balance it, and if it is balanced, then good to go. All right, now we need to insert the values. All right, so insert method will have a type B, which will be a subset of type A, and we will have a value called new value, which will be of type B. All right, this is going to return a tree of type B. But now the trick here is the value B doesn't have any comparison, so we need to have some way that we can compare the values for type B. So we will add the order trait. So how we are going to do it? We'll add it as an implicit for type B as an order trait. Alright, now we can easily do the comparison. It will recognize it. Alright, now we have the inserts done. Next is the traversal. So first is the breadth first search. Okay, so first is DFS. Let's write DFS. Okay, so it is going to be dev in order. So it is going to return a sequence of A, then dev pre-order. Again, it is going to return a sequence of A. Then we have dev post order. It is again going to return a sequence of A. And finally, we have the BFS. That is the level order. So it is going to be level order. That is again going to return a sequence of A. Till now, we have implemented the basic structure. Now, we will use that or use this to create an empty node. So empty node is going to be an object. Alright, it will extends tree. So empty node will be of type what? Nothing, because there is nothing. Now we need to implement the methods that we have. So let's implement all the methods. Alright, one by one. So value, there is nothing, so let's throw an exception. You can do whatever you like, but I am throwing an exception of not implemented and giving a value. Value is empty. Alright, now left tree, because it's an empty node, it's going to be empty. Alright, now we have right, so it is going to be empty again. Height, height will be 0 because there is nothing, so we have a balance factor. Balance factor will also be 0 because there is nothing to balance as of now. Alright, let's go to rotate right. Rotate right is not going to return anything because when we are rotating on the empty node, it is going to be empty. Similarly, rotate left will be empty because there is nothing to rotate. Same thing with the rotate left right, it is going to be empty because if we are going to rotate an empty node or empty tree, nothing is there to rotate. Alright, now we have the balancing. Same thing, it is going to return empty. Same logic as before. Insert, let's keep it as is because once we are inserting the value, it will insert a value and it will create an actual node which is non-empty. Alright, in order traversal, so it is going to be sequence dot empty of nothing. Alright, so let's copy this value. Sorry, let's copy this value and we will be using it. Alright, Same thing for pre-order, because there is nothing, so it is not going to return anything. And same thing for level order. All right, so this completes the implementation of empty node. In the next video, we are going to see the implementation of the non-empty nodes and the traversal techniques. If you enjoyed this video, please like and subscribe, and watch out for the next video. Thank you.